Hello everyone, my name is Santi Gonzalez, or Santi Paprika on the internet. I'm a graphics researcher at Huawei, and in this workshop I would like to showcase how to set up your human avatar visuals in O3D. This workshop is going to introduce some of the most relevant features specific to human rendering and show how to set up them in O3D. Specifically, we are going to target skin, eyes, hair, and cloth. The workshop is divided in 4 blocks, one per feature, and for each one we're going to discuss the physical properties involved, then give a quick overview of the O3D approach to reproduce such material, and finally we'll jump into the O3D editor and showcase the actual material setup. I would like to mention that most of the tools and materials showcased in this workshop are part of a gem that Huawei is releasing soon. I will give more details about this at the end of the workshop. Let us begin with the skin. Skin is translucent. This means that light can travel below the surface and exit the surface at a different point than the one it entered. This phenomenon cannot be modeled with a traditional VRDF, since it would assume that all the light incident at a point is either reflected or absorbed at that same point. Instead, we want to consider multiple exit points for each entry point, or vice versa. This distribution is referred as VSSRDF in the literature. Solving a VSSRDF accurately is very expensive, so O3D approximates it efficiently using a screen space approach. The downside is that it does not account for transmission through thin objects. This involves having to solve transmission on a separate step. The current solution computes transmission using shadow maps. This adds some computational cost but can handle transmission dynamically. An important note here is that since it uses shadow maps to approximate transmission, it is strongly dependent on the shadow map resolution, so having a low resolution is going to output non-valid results. Another feature of skin is that it has an oily layer on top. This, combined with the actual skin layer below, produces a particular specular response that can be reproduced using 2 specular lobes with different roughness values each. The specular outcome then comes from lerping these 2 lobes.
Now let's open O3D and set up the skin shader. I already set up a little scene ahead of time with some lighting and a character. The different materials showcased during this workshop come as material types for you to customize to your needs. I will open the material editor and create a new material for the face skin. Under the materials folder, right-clicking, then create material. Then I can select the material type. I will choose skin enhanced. This is the new material type introduced in this gem. So next I will set a name, face test material, and go ahead and create it. Now let's head back to the editor and set it on our model. This will allow us to edit the parameters while seeing the results in real time. Note that for this I'll be changing the material instance properties, but if we wanted to apply it in multiple objects, we will need to modify the actual material in the material editor. So now let's pin this window here. The skin material exposes a set of textures that you might already be familiar from other PBR materials. As such, I'll start by setting my albedo, roughness, specular, and normal maps, and ambient occlusion as usual. If you see that some properties don't show up when you introduce a texture, you just need to reopen the material inspector. This way, we can now adjust the roughness to look a bit better, and same with the normal map influence. If you remember, in the presentation we described 2 effects, subsurface scattering and transmission. Both of these can be set up in the subsurface scattering section. I'll start with subsurface scattering. First, I will recommend keeping the scatter distance low for skin, since the higher the value, the waxier it will look. Then, in my case, I will also change the scattering color to more closely match the base skin. The other parameters are usually fine by default. Next, I'm going to set the transmission parameters. In this gem, we introduce the Barley transmission approximation, which is an improvement for skin over the already available methods. Same as before, you can set up the transmission color. I would recommend something with a red hue to closely match the shifting color inside the skin. I have prepared a light here to better perceive the transmission. We could further tweak these advanced properties to achieve a better look. If the skin source is close to the object, we can drop the shrink factor. Then, if the light arrives too far from the entry point, we can adjust the thickness factor. Also, the angle bias helps to get a smoother transition between zones with and without transmission, as we can observe here. Finally, let's drop the scale a bit. This is a factor that affects the final transmitted energy. So this looks pretty good, so now we can try to move the light source a bit. Remember that this light requires a high resolution shell map. In this case, it is set to 2K. So if we place it somewhere around here, we can see how some light has been transmitted to the nostrils. Finally, one of the other additions to our skin enhanced material is the dual lobe specular. If you remember the presentation, this approximated the different layers at the surface of the skin. We tried to make as simple as possible for you to configure. First step, we can turn on and off this feature with this toggle switch, and now we have two options to set the roughness of the speculars, and then a slider to set the lerp factor. In this case, a greasy skin would have more contribution from the first lobe, while the dry one would have more contribution from the second one.
Let's proceed with eyes. To properly understand the properties exposed, let us do a quick recap of the eye anatomy. The sclera is the white part of the eye, the iris is the colored part, the pupil is the hole in the middle of the iris, the cornea is the outer layer at the front of the eye, and the limbus is the transition zone between the iris and the sclera. As we can see in this figure, the iris lies on a plane, and the media between the cornea and the iris has different index of refraction than the one of the air. This means that light is not going to follow a straight path to our camera, since it will be refracted in the region between the iris and the cornea. The figure on the right shows the results obtained in L3D. In L3D, we complete refraction using UV coordinates and a specific eye model setup. This might involve a bit of extra work, but it is cheap in terms of performance. So now let's see the requirements. First of all, the UV map must correspond to the frontal projection of the model limited by its diameter, as we can see in this figure. Note that the directions between vertices must correspond as well, so a vertical line in UV space must correspond to a vertical line in the projected front view. Another requirement is that the eyeball needs to be centered at the origin locally, and we need to know the eyeball diameter because it is going to be required information to properly compute the refraction. The same refraction applied to our camera ray applies to the incident light that passes through the cornea, which creates the caustics. Caustics in O3D are applied using a baked irradiance map for different incident angles, and in runtime this only involves a single texture fetch, which is faster than computing the actual refraction. The downside is that it can give inaccurate results in some specific scenarios. We provide a standard irradiance map for a generic eye, but if we wanted to vary drastically the indices of refraction or the iris size, then we will need to bake again all the slices. Now let's talk about reflections. Part of the incoming light gets reflected at the cornea before reaching the iris. These reflections are sharp. However, this is not the case of reflections at the sclera. There is usually some degree of wetness in it, and it distorts the reflections. This effect can be reproduced by using a wavy normal map for the sclera layer, simulating the fluids. As we already know, the pupil aperture can vary with different illumination conditions. What happens to the iris, in this case, is that it gets stretched differently according to the space remaining for it. And this is managed on GPU in O3D using UV stretching on the pixel shader. However, it requires an initial calibration phase to define the initial pupil radius to use as base for the stretching. The limbus has a blending effect between the iris and the sclera, and it is usually a bit darker. To reproduce a proper blending, it is required to provide two layers, one for the iris and one for the sclera. The properties of both layers are going to be blended on GPU according to the size and darkening factors specified by the user. Light can also travel for a short distance in the sclera before leaving. In this case, however, we don't need to be as accurate as before, so we can just approximate the effect with a wrap diffuse, which is much cheaper. Finally, when following a target, the human eyeball orientation does not strictly follow the target. It allows for an angular offset, as we can see in this image, where the fixation point, which would be the target in our case, doesn't need to correspond to the eyeball orientation.
So let's set up the eyes in All3D. First of all, note that I have the eyeballs here in the inspector as separate entities. This is because a requirement for refraction to work was to have the imported asset centered at the origin, if you remember. So we open the material editor and same as before, create material, and this time we're going to select eye material, and I'm going to name it eye test material. Now let's head back to the editor so that we can modify the material there and see the changes in the actual context. Let's pin this window here and let's begin with the iris albedo. So even though we can provide a colored iris, we prefer to input a grayscale version so that we can change the color dynamically through the inspector. In this case, I'm going to import this and use a bluish tone. Then we can assign a normal map to the iris. For the roughness, this acts on the cornea, so we suggest using a small value like 0.03, 0.04 or so. So now let's see the sclera properties. The albedo has no secret. And here for the normal map, remember that we're going to use a wavy map, the one that we mentioned before. In this case, I would like to tune the normal map influence, so I'm going to reload the inspector quickly. And here an important note to make is to make sure to go to the texture menu and then right-click Edit Texture Settings and check that the texture preset is assigned to normals, especially if your texture doesn't contain normal on its name, otherwise the compression format could play against us. Before adjusting the normal factor, we should reduce the roughness here as well for the sclera, and now it seems to disperse, so I'm going to reduce the wave map factor. This looks better now. Here we have some additional parameters for the eye-specific properties. The first parameter you may want to check is the eyeball diameter, maybe even before setting the iris and the sclera properties, just to make sure that it corresponds to the diameter of the eyeball in the original FBX. In my case, it is 1 and I scale it down in All3D, so it is fine this way, but if you scale it down in your DCC before exporting the FBX, then you need to specify the actual diameter here. Then we can choose the size of our iris. And this is the index of refraction. As you can see, let's set it to something smaller than it should, just to notice more the effect. With this toggle we can enable or disable caustics. I have here prepared a sidelight, so this is with caustics, and if we disable them, a traditional Lambertian is going to be used, which looks less realistic. If we want to modify the pupil size, we first need to set this flag to dynamic, and then we will need to calibrate the pupil radius. So in green is displayed the current radius being used to perform the aperture operations. We want this green radius to match with the actual pupil radius. Then we can stop calibrating and we will be able to define the desired pupil aperture. As for the limbus, we can choose the transition size. In this case, I'll set it a bit large. And then I will darken it a bit. We can also enable or disable the use of the wrap diffuse and tweak some parameters influencing it. For the specular reflection, I suggest using a low value to avoid the eye look like a purely reflective mirror. Also, note that we have an occlusion mesh to integrate better the eyes with the eyelids. Here I'm going to enable and disable it. That's it for the material setup, but I would also like to introduce a new component in the gem called Eyes Look At, to reproduce the way human eyes follow the target, as mentioned before. Here you can see, if this is a target, when we move it, how the eyes follow it uniformly. This component can be attached to any entity. We have used a parent entity to both eyes entities, and as you can see, we have the target entity attached. And then for every eye, it is going to be attached to a bone. So we first need to define the actor, which will contain the bone, in this case the character, then the eye entity, which would be our eyes, and then we can select here the bone, which it is going to be attached. And same as with an attachment component, we can define the offset with respect to the bone. We can also modify some rotation properties of the eyeballs, like we can increase or decrease the rotation speed, and we can also adjust the rotation limit. We can also visualize some debug information. In this case, the green arrow corresponds to the direction towards the target, and the orange arrow corresponds to the front direction of the face. If this is not the case, we need to adjust it here in the rotation offset of the attachment, because this is going to be fundamental to compute properly the human-specific eye look at. This parameter defines the shift between the target direction and the actual eyeball orientation.
Now let's go with hair. First, let's do a quick overview of the hair anatomy. This will be a very zoomed in hair strand. Simplifying a lot, it has a cylindrical shape with an irregular surface composed of overlapped scales, which would be the cuticle. The medulla is the core, and the cortex is the media in between. The medulla and the cortex are the components that mainly define the color of hair, and this is because hair is translucent. The shading model used computes the scatter light at a strand level. Because of its translucent nature, again, we cannot stay with a BRDF. However, since hair strands are very thin, we can assume that the enter and leave points for a ray are the same. This reduces the complexity of the problem, so the solution now lies on developing a proper VSDF, which conceptually merges both BRDF and VTDF and is much simpler than a BSSRDF. The actual BSDF details are a bit more involved, so its corresponding parameters are exposed in O3D in a separate advanced option groups. For more details about it, I suggest tuning into the talk that has place on Wednesday called From Wax Figure to Digital Twin, an introduction to human rendering techniques. An important note is that in the case of cylinders and a given longitudinal value, the normal corresponds to a plane instead of a single direction. So this is why the shading model requires the tangent direction instead. To represent hair in our scene, the material introduced expects a hair cards model, which, as you can see in this figure, consists of a set of curved planes and a strand map containing the individual strand detail. This avoids having a very complex geometry. The shading is handled on GPU, so the users can modify the color of the hair with a single parameter and need to provide a strand ID map to achieve individual strand detail. When using hair cards, it is essential to provide an opacity map so that points in the cards without any individual strand information can get discarded.
Let's set up the hairs now. I will start by creating the material. Same as before, I do that in the material editor, but this time I will select the hair material type. Then I'll name it hair test material and save. Now let's head back to the editor and apply it to our model. I will select the hair transparency slot and apply it. Now we can add our material instance. If you recall the presentation, the hair material is using the direction along the strand to achieve the desired shading result. This is the first parameter you may want to set up in your material, and you can find it in the hair section under tangent information origin. We included a visualization option to see in which direction these vectors are going in advanced options. In most cases, though, you will want to set this as vertex by tangents. Now let's take care of our strands. To achieve this, I have a simple opacity map that I will add to the alpha map parameter. If this doesn't show anything, we need to reload the material inspector. And now we can adjust the alpha cutoff point. But first we need to enable the cards to be double-sided. Then we can adjust the cutoff point, and for me something around 0.3 will do perfectly. I would also like to add that this here model has not been prepared for the method that we are using, so this is why you can see some artifacts at the roots here. In a typical production pipeline, we would ask the artists to modify or craft their opacity maps to match the expected input. This is starting to look great, but I find the color a bit too dark. So the hair color is set using this color parameter and it supports a wide range of colors. For now, I will settle on some reddish color, but it still looks a bit uninteresting. This is because although we have the contour of each strand, we don't have per strand details to disassociate them inside a single card. So we can achieve this using an ID map. This is a grayscale image where each strand has a different shape. If on top of this we select the more advanced shading model, this is going to look even better. Finally, some hair colors can only be properly captured with internal scattering of the light. This effect is not currently modeled, but you can achieve a similar result adjusting the diffuse term parameter. You might be already familiar from other engines. I recommend a small value. Also, this material offers more advanced parameters to further customize the look according to your artistic expectations. I would recommend you check the slides if you want further information on their meaning and their impact on the shading. With this, we have achieved a pretty good looking hair.
Finally, let's check cloth. Cloth is composed of microfibers. This slightly changes the interpretation of some PBR parameters like roughness. In this case, roughness modulates how much the microfibers diverge from the normal direction. A typical feature in some cloths is sheen. This is a specular peak at glancing angles due to the waving nature of cloths. In O3D, users can specify the sheen color. Also, depending on the waving pattern and the frequency in each direction, a fabric can have an anisotropic specularity. This is reproduced in O3D as well. And same as with the eye sclera, some fabrics have smooth fall-offs due to the fiber's translucency. Again, this specific case is a very low frequency phenomena which can be approximated with the wrap diffuse. Finally, using detail layers really help to improve the look of clothes at a small scale. The exposed options are base color and ambient occlusion detail layers.
So now let's check the setup of cloth in O3D. Same as with the other materials, we need to open the material editor and then create the new material. In this case, the type is going to be cloth. And we're done. We can head back to the editor and assign it to the proper slot. Then we can open the material inspector and pin it here. As you can see here, the properties exposed are pretty similar to any traditional PBR material. So I will fill this quickly. If you take a look, this already looks fine, and this is because the actual BRDF being used to compute the outcome is different from a traditional one, so it is specific to cloth, but still we can modify some parameters like the sheen color. In this case, it doesn't vary a lot, the outcome, because this material in specific is very rough, and remember that the sheen color affects the specular peak at glancing angles. But we can enable subsurface scattering, the cheap approximation, and see which impact it has on the outcome. In this case, it is more prominent. We can improve it even more if we adjust the subsurface color to something similar to the core of the threads. Finally, even though this is not the best specific scenario to use it, we can apply some anisotropic response. This would make our material to look more a bit like silk, and we can adjust the factor and the anisotropic angle.
So now we're done. Congratulations! We've just achieved a pretty good looking visuals on our human avatar. Before closing the workshop, as promised, I would like to mention that we are soon releasing the Huawei Human Toolkit gem for O3D. This gem contains all the material types that we have showcased in this workshop with all the mentioned features implemented. So we are very excited to share it with the community. For all the details about the gem and more information on human rendering techniques, I strongly recommend tuning into the talk From Wax Figure to Digital Twin, an introduction to human rendering techniques, that has place on Wednesday at noon. Finally, I would like to thank Thomas Poulet for his assistance on this workshop and all the people involved in the first release of the gem. So thank you for joining me, and I'll be glad to take your questions. See you!